And we're live. Hi, Verge.
Hi, Mark. Welcome to Monday.
Yes, Monday. Our penultimate Monday.
Yes, it is. That's true.
All right. So we are Mark Crowley from Ryan High School.
And Verge Cornelius, Lafayette High School, Oxford, Mississippi. There we are on the map with our little headsets on.
Yes. And Friday's still on here. We're actually continuing our mixed bag review today, right? And then those are our
That's right.
topics for the rest of the week. It's actually only topics for 3 of the days. We're wrapping up. This is our last week of review until our exam prep send off, which we'll get you details for that later this week. But next week, we're actually going to start kind of gearing up for that exam. And when is that exam? May 12th at 2 Eastern. And there's your website. There's our format for what we know. We were just discussing how little we know, but we know it'll be a 25-minute question and a 15-minute question, and
it'll be on calculus.
yes, and then you'll be on summer break as far as calculus goes. And 4 days.
Woohoo! Let's see if we can do it on be error-free on a Monday.
Yeah, because I just was going to avoid saying anything just because. All right, so we've done our introductions. We mentioned last Friday. Now that we're into our deep review where we're just gathering topics and kind of scatter shooting, that we're really assuming you to come warmed up. If you haven't gotten it yet, down here, this tabular medley is in the Dropbox. Has been for about a little under an hour, and the 1 through 7 mixed bag review, we're going to finish that up. That was actually in Friday's shared folder, so it's under episode 23.
Yeah.
All right.
Great.
And Verge, are you going to start with that?
I am. I'm going to start with that. Let's see if I can share my screen right now. I'm going to go ahead and, maybe we need to be co-hosts.
Oh, no. I did get here first.
Wow. Well,
or I
guess
can stop
maybe
sharing.
Yeah, you could stop sharing.
All right.
And maybe our producer will make us co-hosts. We forgot to ask her as we were chit-chatting.
You should be able to share now.
Okay.
And she's just made us co-hosts.
Okay. Well, here we go. Well, it's Monday. We've already had
There's our Monday moment, yes.
Glitch, right? Monday moment. Okay. So it's episode 24 of our AP Calculus AB live sessions. And on Friday, we left off with this mixed bag review, which you can find in that Friday folder, units 1 through 7. And this is not the be all end all. It was just kind of a little selection of topics. So unit 3, chain rule, we're going to go ahead and work through these problems, which some of you maybe already worked on over the weekend. Good job if you did. And then also unit 4 and unit 5, we'll take a look at those as well. And then Mark's going to go ahead and grab the screen and start working on that tabular medley free response question. Okay, so unit 3, chain rule. We've got 2 different functions here. The function g is differentiable. The table gives values of g and its derivative g prime at selected values of x. The function h, whose graph is shown above, consists of 3 line segments. So we know a little bit about g and about h. Let k be the function defined by k of x is equal to h of g of x. Find k prime of 1. So right here, I have a composition of functions. G of x is inside of h, so I need chain rule to take the derivative. So I'm going to get k prime of x is equal to h prime of g of x, and then times g prime of x. I'm going to go ahead and substitute in 1. So k prime of 1 is equal to h prime of g of 1 times g prime of 1. So then I have to kind of come up here and look at my table. G prime of 1 is 0.2. G of 1 is 2. So this is the same as h prime of 2 and then times 0.2. Kind of a lot of dots there. Then finally, h prime of 2 is going to be over here. H prime means I need to look at the feature of the graph that is not the y coordinate, but rather the slope. So h prime is going to be the slope. This slope here is definitely a half, up 1 over 2, up 1 over 2. So I can this is equal to 1/2 times 0.2 is 2/10. Final answer, 1/10.
Yay.
Yay! If we've said it once, we've said it a million times. You can leave it like that on your AP exam, but in real life, you cannot. Okay.
So I realized without a warm-up, we didn't get a joke.
But I have a joke, actually. Thank you for reminding me.
Yeah, sorry.
Okay, here you go, Mark. Ready?
That's what was pressing in my mind while I was watching you do the chain wheel.
Pew, pew, pew. Look at your background. Okay. What does a math teacher call a snake that is 3.14 meters long?
Oh, I know where this is going. What does a math teacher call a snake that is 3.14159 meters long?
A python. I throw all the jokes in the sink. I don't know if I told you guys that.
Yes,
okay, anyway. All right, next one. Let m be the function defined by m of g of x equals x. In other words, m and g are inverses. Find m prime of 4. Now, we actually have this phrase a little differently on the tabular medley. So I'm going to go ahead and do it this way using the chain rule. But then when Mark does the tabular medley, he's probably going to talk about something else. Am I right about that, Mark?
Yep.
Okay, so here we go. Take the derivative, kind of doing an implicit differentiation. So m prime of g of x, and then times the derivative of the inside function g prime of x is equal to the derivative of x with respect to x is 1. Now, if m and g are inverses, then m prime of 4, I have to really think about on my table here, do I want this 0.24 that I want to consider, or do I want this 0.48 that I want to consider? And actually, I want this 0.24 because on G, the point is 2, 4, but on the inverse, that would be the x's and the y's get interchanged, so that would be the 0.42. Okay, so really right here, so G of, where am I? So I want m prime of, well, I guess I'll say G of 2.
Right.
And then times G prime of 2. This is all with respect to that G function where 2 is the x coordinate. So G prime of 2 is 0.4. G of 2 is 4. So let's see, I have prime 4 times G prime of 2, which I said was 0.4, and then is equal to 1. So then I'm dividing both sides by 0.4. So m prime of 4 is 1 over 0.4. And 0.4 is 4/10. So this ends up being 10/4, right?
Mm-hmm.
Or 5/2.
And of course, you could leave it in any of those 3 forms.
Yep, that would be fine right there. Strange, but fine.
Yeah, that strange one. Just make sure that decimal point's legible.
Yeah. All right. So that's a nice little table and graph. In fact, this week when we planned our lessons back in March of what we would be doing in May, not even knowing whether or not we'd, we thought maybe we'd be back in school. We didn't even know, but we knew that tables would be important and we knew that a graphical stem would be important. That's why today our lesson was going to focus on a tabular free response question, and then tomorrow on a graphical. So this is kind of like a mini version, little taste of what's going on there. All right, totally separate question here, number 2. It says, given this differential equation, dw dt is equal to 1/10 w minus 600. Find d squared w dt squared, in other words, the second derivative in terms of w. So if I have dw dt and I need the second derivative, how many times do I need to differentiate?
Well, you have to take the derivative of what you have with t once more.
Yep. Just once more. And people do this different ways, but I like to, there have been quite a few of these problems in the past. I like to distribute first, so I kind of have more of a polynomial situation. 1/10 w and then minus 1/10 of 60 is some sort of a number. Or sorry, 1/10 of 600 is some sort of a number at 60. And then I take the derivative of it. So there's my dw dt. And now I have to take the derivative of this with respect to t. So let's see, d squared w dt squared is equal to 1/10 dw dt. So there's that implicit differentiation again, and I've got to be be careful that you're just not writing 1/10 here. So it's got to be 1/10, and then dw dt, the derivative of 60 is 0. Now, it says in terms of w, which means though this is a correct answer, it wouldn't earn full credit because I need to replace dt with 1/10 w minus 600. So final answer would be 1/10, and then in parentheses, 1/10, and then w minus 600 in yet another smaller parenthesis.
Yay.
Yeah. So, sound good, Mark?
Sounds good.
Okay.
I want to apologize. You probably heard me try to.
Oh, I heard you yawn.
I got up early to go to the grocery store today, and I didn't think it would hammer me as bad as it is. So.
Did you take advantage of those senior hours, Mark?
No, those are Sunday, Tuesday, and Thursday. I intentionally avoided them. I don't qualify yet, so I didn't want to get there right at 7:30 when it switches over and have people like, "Are you trying to sneak in?"
Yeah, well, we have those on Monday through Thursday in our community, at 7 to 8 a.m. I think it is. So yeah.
Yeah, ours are 6 to 7:30 on those. What I think of as the even days: Tuesday, Thursday, Saturday.
That's good. All right, Unit 4, second page, contextual applications of the derivative. So this is an application of the derivative with a story, basically. So here's the story. At the beginning of 2020, a landfill contained 1,500 tons of solid waste. The increasing function W models the total amount of solid waste stored at the landfill. Planners estimate that W will satisfy the differential equation dW dt equals 1/10 W minus 600 for the next 10 years. W is measured in tons and T is measured in years from the start of 2020. Use the tangent line to the graph of W at T equals 0 to approximate the amount of solid waste that the landfill contains at the end of April, time T equals 1/3. Ooh, lots going on here. But I saw this, and so I think I need to write an equation of a tangent line. I need two things, slope and a point. So this is my recipe for the slope, the formula for the slope. I need to go ahead and plug in something for W. So let's see what I have here. At the beginning, the landfill had that many tons of solid waste. Mathematically, that's W of 0 equals 1,500. So I can plug in 1,500 W here to figure out my slope. So dW dt is equal to 1/10 times 1,500 minus 600, or 900 over 10. How am I doing? I know I kind of blipped out there a little bit.
I was actually thinking this is the one time as a math teacher you're not allowed to get offended when a student says, "So what's your point?"
Does that write for the slope 90?
I can go check my key. I haven't done this since last Friday, but
I know, me too. I should have done it this morning.
1,500 minus 600 is 900. It feels good.
Okay. So then let's see here. I need to write this tangent line, and I'm going to just use y's and x's for that. I mean, some people might argue that I should be using appropriate variables, but y minus, let's see, this is my point right here. So y minus 1,500 is equal to my slope 90 times x minus 0. That's my attached to that graph at that point. And then I'm going to substitute in 1/3 for that x value, that t value. So let's see here. That would be, y is equal to 1,500 plus 90 times 1/3 minus 0, or y is equal to 1,500 plus 30, 1,530, and I believe the W is in tons. Again, you can really leave it like this, but this is a perfect example of check the reasonableness of your answer. You know, they're putting garbage stuff, you can imagine what I'm thinking in my mind, into a landfill. They're putting it in. So of course, this amount in April or at the beginning of April has to be more than what they started with. So if you made a calculation error somewhere and you're ending up with 14 something for your tons, you know that you need to kind of quickly go back and see if you can figure out where you went wrong. If you leave it like this, you may or may not know that you ever made a mistake. So checking the reasonableness of your answer is key. Anything else on that, Mark?
No, I don't think so.
Okay. All right.
I was looking for a key and I don't think I have one. So
okay. Well,
I thought I typed one up, but I worked them. I thought I typed
you did type it up. I usually watch you type them up, but
yeah,
I don't know. All right. Unit 5. Now, this is the last one we're going to do today, is the top part here, just this first one. That doesn't mean we might not come back to these other two another day. We do want to get into that more tabular heavy lesson, though. The analytical applications of the derivative. So this is kind of like, how are you allowed to say that? What's your reasoning? What theorem are you appealing to? How can you conclusion based on given information and that kind of stuff. So this is the same contextual problem, but now we're asking really an analytical question about it. So it says here, it's exactly the same as what I just read, and it's exactly the same up until here, actually. And then it says, find the second derivative in terms of W. Hey, wait a minute. Didn't I just do that? Or was that, I did just do that. Use that second derivative to determine if the tangent line approximation is an underestimate or an overestimate of the solid waste. Okay, so let's see. We got the second derivative, d squared w dt squared, to be 1/10, I'm importing from the other side.
Right.
Times 1/10 w minus 600. And so this ends up being, let's see, 1/100th times w minus 600, or 1/100th w minus and then 6. So what do we think? How can I use this information to answer the question? Use that second derivative to determine if the tangent line approximation is an underestimate or an overestimate of the solid waste that the landfill contains at the time t equals 1/3.
Well, I think we actually have to look at dw dt for a second.
Okay.
Because I know that at time 0, I had 1,500 tons.
Mm-hmm.
And so that value, that dw dt, is never going to be able to be negative because it's positive. So the amount of waste I have is going to go up.
Mm-hmm.
And that's important because that means the number I'm plugging into w in my second derivative here is larger than 1,500.
Mm-hmm. So for t greater than or equal to 0, basically.
Yeah, I can say that's positive.
We can say that the second derivative is greater than 0. Therefore, how is the therefore, what do we know about the tangent line? Is it going to be kind of underneath the function or above the function?
I always just draw a quick sketch.
Mm-hmm. Okay, so second derivative greater than 0, that means concave. This is what I'm thinking in my head.
Yep.
And then I kind of put my little tangent line like that. And I say, oh, that means a tangent line estimate is actually a little bit less than the actual value. So therefore,
and even on the downhill side, right? It doesn't matter where you are on that concave up curve, your tangent line will be under it. And some of you may know that better because some of your books will actually define concavity that way. The concave up is always curving up away from the tangent line.
Okay. So let's see, do I need to write anything else? So for t is greater than or equal to 0, the second derivative is greater than 0, therefore tangent line under approximates the actual
at t equals
value at t equals, I always run out of space, t equals 1/3 year or something like that. How's that, Mark?
That looks good.
Okay. If you are a teacher watching, and I know that there are teachers watching, you know this problem because it's the landfill problem from, I don't know, like 8 or 10 years ago, but I changed
2011.
I changed the numbers on it. So
Yep.
like you can go back and find that problem and see the other numbers. There's also, I think, a separation of variables to solve for that differential equation, which would be a great exercise for students and teachers to do. So other ones on that, are you going to go ahead and grab the screen, Mark?
Sure.
Okay.
And I want that one. All right. There's my blank version of that. Okay. So hopefully you've gone and gotten it. If you haven't, you can pause it or go get it later. But this is the document that is in the Dropbox. It is, we called it Tabular Medley. And we sketched this up and it came into fruition yesterday, but it has J parts. And I think this is much more than a normal free response, but we just kind of said, hey, how much stuff can we do with this table? And
right. This is way more than even that 25-minute question would
absolutely.
ask. But I mean, you know, it's like a buffet. It could ask any
That's
6 of these questions probably,
exactly.
right?
So we're just going to jump in. We didn't discuss an order, but I'm just going to start working my way down the page. We've got 25 minutes. And if I get tired, I'll tag Virgin. But the function f is twice differentiable. Sorry, I said it like it was a command. Select values of f and f prime are given in the table below. F has exactly 2 critical numbers on the interval 112, and you can actually spot them because where do critical numbers happen?
Where the first derivative equals 0, or where the first derivative is undefined, but the function is
nice.
Is defined. Yeah.
Exactly.
I mean, it's so awkward to say it. Can we come up with a better way of saying it? I don't know. But yeah.
I always say where it's undefined and in the domain of the function.
So
because asymptotes aren't critical numbers, right?
And when you say it, what you mean is where f prime is
undefined. F prime is undefined, and the value of x is in the domain. That's of f.
So at 2,
actually of both at that point. But anyway, so 2 and 7 are our critical numbers, so we can see where they are. So we know that there's no change in sign anywhere else because those are the only places it's 0, and since it's differentiable, the derivative's everywhere. Use the table to approximate f double prime of 6. So I'm really finding, and this may make some people cringe, but we're really finding f prime prime, right? And so we're looking for the derivative at 6, which is right here in our table, which is not in our table. And so we're going to take the closest interval around 6 that we can. And so we're going to estimate the derivative using this. I am going to put that in a thought bubble because I know that prime that way is going to disturb some people. I guess I could have written it as ddx of f prime. Actually, I'm going to change it.
This is why we never finish the lesson.
Because I want it to be mathematically correct. Okay. In any case, so we want to approximate this. And how do we approximate instantaneous rate of change? With average rate of change.
Yep.
Yeah.
But on as close as we can get. Right. And AP, we generally kind of take 1 point on either side is the convention.
Yeah. So it's been several years since you couldn't actually, and then they accepted like 3 different answers, and they haven't done it since. So I grabbed, it's again y's overrun, right? So I grabbed my y values, which in this case are the f primes, and I'm going to do 0 minus -2 over 7 minus 5, and I get 1. Of course, I could stop here, right? And so our approximation of that slope is 1. So it's going uphill. That seems weird, but it's the second derivative. Oh no, that's not bad, right? Because it's going from negative to positive, so it should be increasing. So yeah, I like that. That's positive 1. Good. Not that anyone else cares, but I like to check. Oh, I care deeply. Okay, so B, and we've done a trapezoidal sum. Which way do you think I should do this one, Virg? You want me to do straight trapezoid, or do you want me to do a left and right?
Well, you've practiced left and right and then taking the average, but why not do straight trapezoid since you did make a mistake on the left and right?
I did do a mistake.
The average this morning.
So it was yesterday afternoon, but yes.
Okay.
And I am fatigued from my arduous trip to the grocery store. So we're doing from 1 to 10. Now, you have to be careful to read here. And I did this, and I've seen this on AP, right? They didn't ask for 1 to 12. They asked for 1 to 10. So the 4 subintervals are going to be 1 to 2, 2 to 5, 5 to 7, and 7 to 10. So I'm stopping here for my question B.
Oh, and you know what? Here's a good question. One of the teachers said, my students get confused. When should they use fundamental theorem of calculus, and when should they do a trapezoid or left-hand sum? And I think somebody had answered, if you're asked to approximate, chances are you're doing some sort of a trapezoidal sum or left-hand sum or right-hand sum or midpoint sum. So that word estimate or approximation will tell you you are not using fundamental theorem. You are, you are doing that. Okay.
And I just went ahead and reminded myself the area of a trapezoid is 1/2 the sum of the bases times height, or the average of the bases times the height. I know some people put that over too. Just a reminder that our trapezoids, and if you think of traditional trapezoids, they usually should draw the parallels as the top and bottom bases, right? Our trapezoids are actually sideways if we tilt our paper 90 degrees. So those are the function values, and the height of my trapezoid is actually what we think of as the width of the interval. So I'm just going to do 1/2, and my 2 bases are going to be, I'm looking at F, 2 plus 4, and that width is 1, 2 minus 1. Actually, I'm going to go ahead and write it. And if I'm going to actually factor that 1/2 out.
Mm-hmm.
And then my next 2, and I'm just walking across these values, 4 plus 2, 5 minus 2. So the 2 function values, and then the width of the interval.
This is the first time we've done a
2 plus 5,
trapezoidal this
yeah.
way on our lives, but
And
many
7
of you
minus 5.
maybe have done it this way in class.
And then the last one is the 5 plus 7, and 10 minus 7 is 3. And one of the things I always check for on traps is you're going to use, the borders are going to get used twice. So 2 plus 4, 4 plus 2, 2 plus 5, and then 5 plus 7. So. And I could leave it like that. I think I'm going to leave it like that. I can do some waving of hands in that, but it should equal 37 if I did it correctly. So I think that's 6, 18, 24.
He can't ever leave it
I
like
can't,
that.
no. 38. 36, 70. Yay, 74. Half of 74 is 37.
Yay,
All right.
that was fast.
And of course, you can use a calculator to evaluate that if you wish. And you're still going to have to show this step because it said to use trapezoidal sum. So you're going to need to show this step right here before you jump to a number in any case. So I would just write that and walk away on the exam. But you're right. In the back of my mind, I'm always checking it. Okay, so for C, and I'm going to have to start doing some magic folding here, or bring my table down. It says, find the integral from 1 to 12. Actually, I think I can manage this one. This is where I should have had you say the joke. I could have cut that table off while you told the joke.
I've got about 20 more.
Oh, good. I'm actually going to do this for this one. So I am going to break this into 2 intervals, or not two integrals, I'm sorry. F prime of x dx plus the integral from 1 to 12 of 2 dx, because that is going to be a little easier, isn't it? I can break that up because I can use fundamental theorem on this. What's the antiderivative of f prime, Virg?
F.
F.
Yeah.
So this is just f of x from 1 to 12. And if I want to do this using derivatives or antiderivatives, this is 2x from 1 to 12. I would actually just do 11 times 2 because that's a rectangle. Not to scale.
Not to scale, shaded in. There you go.
Yeah. But this is going to be f of 12 minus f of 1, and then 24 minus 2, or just the 22, which is the 11 times 2 from that. Going up to the table, I find f of 12 is 9. F of 1 is 2. I can stop there, or we can say it's 29. All right.
And I think that's a nice contrast to B, because both of them are definite integrals, but the method of calculation is totally different based on the prompt. The prompt being just find versus approximate. And also I love oh, he's just doing a lot of, he's selling another couch. Okay.
If anyone never heard of knows where the phrase is cut and paste from, that's where it actually comes from.
Yeah.
Cutting and pasting before you hit the photocopier. Yeah.
Yeah.
All right.
I love question D. If you are watching in Arizona, this one's for you.
Nice. Also, I need to tell people, if you want me to read your text messages, if you're trying to get important information to us during this, don't send pictures, because we don't get picture previews. Someone texted me something. Oh, that's.
Of course, my phone's completely in airplane mode right now, because I have to steal the Wi-Fi from the house to broadcast.
Nice. Well, it's Monday, which is middle school day in my district, so I'm getting a bunch of texts from my son's Google Classroom as well. All right, so here's our table again, and now it says verify that this limit as x approaches 12 of the integral from 1 to x of f prime of t plus 2 dt minus 29 over 6 minus 72 equals a half. So we know the answer, right? We just need to verify it. Now, this should look vaguely familiar, because the first way we should try to evaluate a limit is substitute. And if I plug 12 in here, the integral from 1 to 12, well, it doesn't matter if both x's have become t's. The integral from 1 to 12 of that expression is going to be 29. And 29 minus 29 is going to be 0. And in the denominator, 6 times 12. What is 6 times 12, Verge?
I hope it's 72, because that's what I told you to put this morning.
When we changed the problem, yeah.
We changed the problem, yeah.
So that limit equals 0.
Oh, he's making a 0 sandwich.
Yep, making a 0 sandwich. Low calories. All right, so you're so easy to amuse sometimes. All right, so this limit is equal to 0.
I need one of those sandwiches.
Is equal to this limit, which is equal to 0. And that means I can use L'Hopital's rule, right? I almost said hospital. L'Hopital's rule. And so I'm going to take the limit as x approaches 12. And they said to verify, so I'm going to try and show everything well. I'm not doing everything I would need to do, I think, to justify, but I'm definitely going to support all my work. So now using L'Hopital's rule.
Yeah, he's saying therefore this limit equals this limit. Yeah. He's going to put the derivatives.
The derivative of that. So we're looking at fundamental theorem. So the 1 is going to become a moot point, because if I plug in that 1 into the antiderivative and take the derivative of a constant, it's 0. But I take the antiderivative of this, I plug in x, I take the derivative. I'm going to get f prime of x plus 2, the entire integrand. And then I chain out the derivative of x, but that's just 1. So over the derivative of 6x minus 72, which is 6.
And by the way, that minus 29 up in the numerator is not part of that definite integral. So when you take the derivative of it, it's 0. Like derivative of minus 29 ends up being 0. So that's why he doesn't have anything written down there. That
dt ends that statement, or at least that operator. And then f prime is a continuous function. F is twice differentiable, right? So f prime is continuous. So I can just plug in that 12 and evaluate. And f prime at 12, if I push my table down, at 12, f prime is 1. So 1 plus 2 over 6, or 3/6, or a half.
Nice.
Yay.
Could be my favorite problem so far.
Really?
Yeah, I love it. I love it.
All right. So I gotta get out of I think I'm over here somewhere, right?
You're good.
Write an equation of the tangent line to f at x equals 10. Use this line to approximate f of 11.
If there's not a tangent line question on this AP exam, I'm going to be mad. because our kids know how to do them,
I was
right,
gonna say,
Mr. Corrali?
not nearly as bad as the thousands of students that are watching us. Okay, so tangent line, point, slope. And they want me to at x equals 10. So f of 10 equals 10, 7 is my point. And my slope will be f prime at 10, which is 3/2.
Mm-hmm.
So my tangent line, again, I use that Taylor form or shifted form. And I left that m off. Okay, so y is going to be 7 plus 3/2, 10 minus x.
Why 10 minus
x minus 10? Because I started reading ahead.
You were thinking about substituting that.
I was thinking, yeah, I was okay, so there's my tangent line, and they did say to write the equation, so I have to present that. And now we're going to approximate f of 11 using that. So 11 minus 10 is 1. Perfectly good. Also perfectly good.
Yeah. And I like that Mark has f of 11 is approximately yada, 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 but you don't even have to say that, honestly, on the AP exam.
No.
Mark, with your finger, go ahead and cover up f of, yeah, all that would have been happy. Like that's
and y equals and f11 equals would have been fine because they told you to find an approximation, and then you're saying my approximation is this. And I mean, it's nicer if they're correct, but
yeah, it'll always be correct on like the AP answer keys and things like that. Not that, yeah, it'll be like super correct.
And have a dozen eyes on it before it moves anywhere.
Mm-hmm.
All right. What is the least number of times f of x can equal 3 on the interval from 1 to 12? And that's our entire interval, correct?
Yes.
And it just says explain, which is a lower bar than justify. We're allowed to put this into our own words. I have typed up my reasoning for this, and I think it's actually overkill the way I wrote it up. But we're trying to find out if it equals 3. So I'm just going to look at my values of f. We start at 2, we go to 4, we go to 2, we go to 5, we go to 7, we go to 9. How many times do you suspect we hit 3?
Any time that those y values cross 3, basically.
Yeah. So like from 2 to 4.
And
then
also
on the way back.
That's exactly how I wrote mine this morning. Yep. And then on the way back. Yep.
And then on the way. Now, it doesn't mean the function is always in between those two values. Although this one is, we can say it, but you know, if this information at the top wasn't given, these might be oscillating even in between. But we actually know these are our only critical numbers. And then when do these happen? And so I'm going to go ahead and say for x, let's say for x between 1 and 2, what is that? I'm going to actually say, let's see, I'm going to rewrite it. This is my thinking process. So I'm going to say 3 times. Let's go ahead and commit to our 3.
Yeah, and now
we can't guarantee it between 5 and 7, 7 and 9.
Now you can kind of also state your conditions for why.
Yeah. And now I'm just going to replace those. I'm going to say for x between 1 and 2, f of 3 is in between f of 1 and f of 2.
Although it would be fine to have a 2 is less than 3 is less than 4.
Oh, yeah. And then from 2 to 5. Because this one I do go kind of the backwards way, right?
Mm-hmm.
And then from 5 to 7. And this is important. Since f is twice differentiable, f is continuous on 112. So what is this? Intermediate value theorem?
Mm-hmm. Which you don't have to actually say. Nope. You don't have to name it as the intermediate value theorem, but like that's what guarantees that we can have at least 3 times.
Yeah.
Yeah.
Like I said, that's probably not totally airtight. I'm sure someone will email me a mistake somewhere in here, but it's explain your reasoning.
Yeah, so I think it's fine. Okay. Yeah. But if you didn't have the fact that you talked about differentiability implies continuity, then because we could just have like a function that's just a bunch of dots, like a scatter plot or something.
Right. Yeah, or you could have it an asymptote or a jump discontinuity, all kinds of stuff, right?
Yep.
All right. So G, G, like K of X equal F of 2 of X, F of 2X, sorry. Find K prime at 5. So, and again, a lot of these problems are going to look familiar. Verge did problems like these earlier, but they weren't always tabular, right? So just we're playing with things you can do with tables today. So when I take K prime, I'm going to do F prime of 2X. And then my little mental check, those internal dialogues we talked about, I think going back over a week now, is this just X in here?
Nope.
Nope. So you take the derivative of it.
You know, even if it were just X in there, you could take the
still chain
derivative
it.
of it. Yeah.
Absolutely. So K prime of 5 is going to be F prime of 2 times 5 times 2. I'm going to go ahead and skip a step here. So F prime of 10 is 3 halves. The sound effects help so much. And again, 3 halves times 2 would be okay, but we're going to go ahead and call it 3. All right. I've got 5 minutes. Do you think we should try to get through all this, or at least get through
I think do H, and then we can kind of, they can
we could even leave I and J. Yeah. All right.
They can do those.
H is an inverse. Okay. So, and I love the way Verge did her inverse, because I think that's the way a lot of you are going to have to do it on May 12th if it shows up, because you don't remember the formulas and the tricks. But if you happen to be watching this video on May 11th and this sticks for you, this is really nice. So M is the inverse of F only on the interval 7 to 12. That's because from 7 to 12, this function is always increasing. We have all positive F primes there. This isn't a one-to-one function, so we can't have an inverse for its entire domain. But it's the inverse on this domain, and we want M prime at 7. Well, if you remember what Verge did earlier, she did a little, was it M of G in yours?
Yep.
It was M of G of X
equals
X because they're inverses.
Yeah, that's the definition of inverse. Like from an algebra 2 or pre-calculus class, like you would have had that on the board.
Right. And so this is the big thing for me, is this is what I always remember and try to think about is if you solve for M prime, it's 1 over G prime at X, which is not, those are the same X's, right? This is specific X. It's not the 7. So what I have to do is I have to go find for mine, it's going to be 1 over F prime at wherever that 7 occurs, right? At
like
M of 7.
M of 7, yeah.
It's M of 7, yeah, because it has to be where that, because what happens with an inverse, right? What gets inverted?
The domain and the range get interchanged.
Domain and range get inverted. And as far as the slopes go, or the derivatives,
this is the coolest part of all.
Right, it's the reciprocal.
Yeah,
so.
yeah. It's not the opposite reciprocal. It's just the wholesale numerator denominator swap.
I just have to find out where 7 occurs on F. And so I'm going to go across F until I see a 7. It occurs at 10, which is in the interval I want. And so I'm really finding F prime at 10. And this is the part I think is so cool, is once you're on the table, you stay for the same value of X. If this is where F of X is 7, then this is F prime at 7. So you're just like, ooh, 10, boom, 3 halves. And it's 1 over 3 halves, or 2/3. And so I was like, where's it happen? Derivative there, reciprocal. And again, I know some of you won't remember it on test day. It won't be a big deal, but if you remember it, it makes it so easy. It's just cool.
And how to recognize that you're being asked about the inverse, you know, like you see either the word inverse, or you see that -1 exponent, or you see the explicit, you know, M of G of X equals X.
That kind relationship.
Yep.
All right. Well, it is 1:44. And
so the
next two go really well together. So I think we should leave them.
We'll start with those tomorrow for sure. So that's your warm up. Get them done in addition to other things that you might be having yourself do practicing.
Keep talking while I get the slideshow ready.
Okay. Yeah. Like don't just do these 2 problems for before tomorrow. I'm sure your teacher has some suggested practice, or there's things in the Dropbox from last week that you haven't finished. Or you can go online to different sites and do practicing and things like that. So
tomorrow we will finish those, right?
Right, those 2, yep.
And that maybe we'll even call it the warm-up again. We have a return engagement of the warm-up. And then we're going to talk about graphical stems primarily tomorrow.
So that means when you've got a graph, and then you're asking a bunch of questions about that graph or the related function.
And again, all these materials are in that Dropbox. There's the bit.ly right there if you need to write it down or type it. Aim your camera at that QR code or go down where it says show more in the description, and there's a link there every day. Thanks for watching.
Yeah, we're so happy to be back. It's weird to have a weekend where I don't actually do a live session. I kind of was a little bit out of sorts today, like, what am I supposed to do? Like, oh yeah, here we go.
All right.
So
and here we go.
And here we go. You got to do that last slide, Mark, right?
I know. All right.
Okay.
Bye, everybody.
Bye. Thanks for watching.